Doing today? I hope you're having a good time. I hope it's afternoon or good morning. I always have trouble with that. So this is Dr. Mandis coming at you to talk about the pH of acids, bases, and buffers. Just a little bit of just pH. I want to do a quick little review with you. Hey, what's an acid? What's a base? What's a pH? Really fast. Look, acids and bases come in two varieties, weak and strong. The way they differ is in their dissociation, which we're going to get to in one sec. But the weak acids will have a Ka, weak base have a Kb based on that dissociation. You may have to look them up, maybe give it to you. The problem just depends. The easiest way to tell if something's weak or strong is to know if it's strong. And if it ain't one of them, by default, you got yourself something that's weak. The strong acids are listed right there. There are 6 of them in the universe. Sometimes people try to convince you that something else is a strong acid. It might be strong, but by our definition of strong, it's 100% dissociated. Some acids come close, but only those 6 are fully 100% dissociated. For H2SO4, it's only for that one H, not for both. Strong bases are your metal hydroxides. Those metals that are listed there with hydroxide would be soluble ionic compounds fully dissociated in water, so this would be your strong bases producing hydroxide. Your weak bases would be any anion other than the 6 that come from the strong acids. But they're also amines, and amines are these organic groups that have nitrogen in them. I have 2 examples there. One is your acetate, and the other is ethylamine. But remember, if it's not on the strong list, it's weak, and move on from there. Right? Acid-base dissociation, if it was strong, those equilibrium arrows that you see there would just be a regular arrow. But these are talking mainly the weak guys, so you can see where the equilibrium comes from. Acids and bases have equilibrium, so they get to the equilibrium expression. Acids produce hydronium. On the base side, you're producing the hydroxide. Water, remember, is not included in equilibrium expressions because it's a pure liquid. Pure liquids have an activity of 1, and equilibrium expressions are based on activity, so the 1 doesn't need to be done. But you don't need to know all that. You just need to know pure liquids aren't used. At equilibrium, if you look at the stoichiometry of that, and under acids, the A1 negative, the base, and the hydronium are going to be equal to each other, and they'll have the value of X, some unknown value that we're going to solve for. For the bases, the HP positive, that conjugate acid, and the hydroxide, well, they're going to be equal to each other. Whatever that value is, that's X. We're going to solve for that. So if you look in those final expressions, I have X times X, either over the concentration of the acid or the concentration of the base. Those would be the original amounts, because since they're very weak, we're only having a little bit of dissociation here, and so the original amounts can go in. We don't have to worry about subtracting off the amount that dissociated. If you had one of those guys that were like 90% dissociated, we would, but we are not going to do that, okay? And basically then we can use those to solve for hydronium or hydroxide according to the following. Strong acids, weak acids, you get your pH both. For the strong acids, the pH is just a negative log of the hydronium because hydronium will be equal to the acid concentration because of the stoichiometry. It's 100% dissociated, so they're going to be equal. Weak acids, before you get to the negative log of the hydronium, you have to get the hydronium, and that's where you solve for X out of the equilibrium expression. Same gig for the weak bases. You need hydroxide. We'll solve for X and get the value of the hydroxide. Then do what you did for strong bases. And they're strong bases, since we have hydroxide, we do a POH instead of a pH. No big deal. Just take the negative log of the value. But big deal. It's 14 minus the POH to get to the pH. Okay. Some schools, some teachers will get the hydroxide concentration to a hydronium concentration and redo a pH. I think my experience as a teacher, that's not the most efficient way to do it for students, so we do want to have there. Just realize that you got to differentiate. Do you have an acid or base? Do you have strong or weak? And just go from there. Don't get caught. Don't be wanting to see everything all at once. Again, just slow yourself down. Acid or base, strong or weak, and just apply the right equations. But what if you got both? If you got both, you got a buffer. Sounds more complicated, but actually, once you get into it in a couple slides, it really isn't. A buffer is a weak acid and its conjugate base. The example there, you see that they only differ by the H. I have KNO2 there just to bring up, hey, in a problem, you may see the whole ionic compound, or in the lab, you see the whole ionic compound. But ionic compounds dissociate in water, and that counterion, the cation, goes away. So KNO2 is really NO2 negative. So HNO2 and NO2 negative, they only differ in H1 positive, so that's a weak acid, conjugate base, that's a buffer. So you got both is a buffer. And it's the only time you're going to have to give them both in a problem. So that's when you got a buffer. So how to calculate the pH of a buffer? Woo! How to make it look complicated? Well, plug in your concentration of your acid, plug in your concentration of your base, solve for X. You could do that all over again. But if you let me derive something, you'll have to make your life easier. Ka expression, cool. Take the negative log of both sides. Then on the right-hand side, since you have a division, or multiplication, I should say, we can add in and separate out those two negative logs. Remember, p is negative log. So for two of them, I'm going to substitute a p, but not for the ratio. I'm going to keep that as a negative log. So hang tight. Just follow that. Negative log both sides, breaking up the multiplication, adding in the p for negative log. Okay, rearrange that. We get what we call the Henderson-Hasselbalch equation. pH is pKa plus the log of the ratio of conjugate base to conjugate acid. To calculate the pH of a buffer, then, you just need to sub in your values of Ka and your two concentrations of your conjugate base and your acid. Well, if that's what you got, then that's all you got to do. The only way two people screw this up two ways. If you're given a Kb instead of a Ka, you need to convert Kb to Ka using the ordered association of water using Kw. Because Ka times Kb is Kw. That's on a different video, but you can refer back to that in your notes. As far as the ratio goes, sometimes students plug things in the wrong way. Always write out a general equation. Always realize that your acid is your bottom. So your bottom's your acid. So put the acid on the bottom and you'll be good to go. Doesn't matter which is given first, base or acid. Acid's always on the bottom. Doesn't matter whether you got a Ka or Kb. The acid is on the bottom. For the Ka, make sure it's a Ka, not a Kb. Two example problems and we're out of here. Example problem number 1. Calculate the pH of that solution of 22 molar acetic acid. Realistically, all you have to do, X times X over the concentration. But I just thought I'd show you the isostatement association just to be thorough. You don't have to write all that. It's always the same. But there's your Ka. X times X over 0.2. X is really small, so you can just leave it as 0.2. You get X to be 1.9 times 10 to the negative 3. I didn't show it here, but the pH would be the negative log of that 1.9 times 10 to the negative 3. If you did that, it's 2.72. If you want to save time and not write pH equals negative log of whatever, I'm cool with that because I know you're just typing it on your computer. But if you want to write it out, I'm cool with that too because I love it when you show more work. But it's getting really busy, so I didn't show it on this particular slide. Example problem number 2, I thought you should see the buffer. Say pH 40 mils of a solution, they got 5 millimoles of acetate, 15 millimoles of acetic acid, and there's the Ka. You know you got a buffer because here you're given both things. Since you have both, use the Henderson-Hasselbalch equation. pH pKa plus the log of the ratio base to acid. I plugged in everything in my gig, negative log of the Ka plus the log. 5 millimoles over 40 milliliters would give you a concentration in moles per liter. 15 millimoles divided by 40 milliliters would give you also a concentration in moles per liter. So you can do all that math if you want. If you pause for a minute, you would see that the 40 milliliters cancels out. So you didn't really have to do that math. You can just plug in your value of mole or millimole, just so they're the same, and your units will work out, and you'll get your pH. So if you like this, hit like. If you didn't like it, if you're my student, hit like anyway. Anyway, love you guys lots. Have a good time. Hopefully this will help you out. Take care.